Today I'm going to talk about learning in NARS. Especially I will try something different. I will try to use a couple of concrete examples to show the difference between how learning is carried out in NARS compared to conventional machine learning systems. First, some basic, I think most of you are already familiar with this, but still let me start from here. Knowledge representation, since NARS is a reasoning system using a term logic. The basic component of representation is what we call a term, which is just an internal identifier of a concept within the system. In the simplest case, it just can be a string of any character. In this following example, I will use English words, but it doesn't really have to be the case. Then from term, we can form a statement. The simplest case, again, the statement is formed by two terms. One subject term, one predicate term are related together by a copula. So it's very similar to the format used in Aristotle's logic. Then what is a copular? Well, there are several types of copulars. In NARS, the most fundamental one is what we call inheritance copular, which intuitively represent specialization or generalization relationship between two concepts. Okay. So graphically, we can say, okay, there is inheritance from a S to a P where both terms. A concrete example will be, say, for example, water is a type of liquid, is represented as a statement with water is the subject term, liquid is the predicate term. The relationship is the copular, which is a type of, roughly speaking. Then inheritance, by definition, is reflexive and transitive. That's kind of like obvious. It idealizes the situation at least. Then this is begin to be different compared to the other system. Truth value. Okay, we know that in NARS, truth is based on evidence. So that for this statement, as there is an inheritance relation from S to P, the truth value is represented by two numbers, both between their own one real numbers. And the first one is what I call frequency, is the proportion of positive evidence among all evidence. Of course, here we assume there is a way to identify and measure the amount of evidence which is given in my publications. Here, I'm not going to explain in detail. It just intuitively, you can just think, okay, this relationship is tested once, and the result is positive, meaning that as far as that testing goes, this relationship is true. Okay? And then you can test it again, maybe that second time is false, and then it becomes negative evidence. Anyway, this is positive evidence. This is the total amount of testing, intuitively speaking. So this is very similar to probability, even though a probability is defined to be the limit of frequency, but in NARS, it does not take limit. It's just whatever you know at the moment. Then the second one is special, is unique in this system. It's called confidence measurement, which is a function of the total amount of evidence. That's what you have tested compared to what you're going to know after the next testing. So that's why W is compared to W plus 1. So you're taking the future situation into consideration. So confidence value in the system, according to this definition, is always less than 1. But it will become bigger and bigger when you have more and more evidence. Okay. So a statement plus its truth value altogether is called a judgment in the system. So based on this simple knowledge representation, now we can begin to introduce the inference rules. For example, the simplest case is the deduction rule. So you have two judgments, and from them you can derive a new one. Intuitively speaking, you can see this graphical representation underneath, so which is just nothing but the transitivity of inheritance extended from binary to a multi-value situation. So if this tool is both premise and matter of degree, then the conclusion, of course, is also a matter of degree. And how to calculate that, we have truth value functions defined in the system. Again, the justification is in my publication. So the basic idea is to extend the binary Boolean operator into real number operators. Then this is a concrete example. Say if this to a premise, we're taking the default truth value used in the system. So it's completely true, but to believe to a certain degree. Then the conclusion is also completely true as far as the evidence goes. Also believe to a degree which is lower than the degree of the premise. Okay. So this is pretty straightforward. And then we have non-deductive rules like inductive rule. And here, the two premises have a different combination. Here, the shared term is the common subject of the two premises. Then you can still get a conclusion in NARS. It just the confidence level you can see is lower than the confidence level of deductive reasoning. It's kind of like you have evidence which support your hypothesis to a certain degree, okay? But it's still justifiable in NARS. And symmetrically, we have an abductive rule or abduction rule where the common term or the common predicate of the two premises. Again, you can get hypothesis supported to a certain degree. And finally, we have a revision rule where if you have two judgments with the same content or the same statement in it, but a different truth value coming from different evidence, then you can merge the evidence or pool the evidence together so to get a summary of the two. This is basically based on the addition or summation of the positive and the total evidence of the premise under the assumption that no evidence is used in both premises. So this is an example. You have a positive, you have a negative, then you get something like a weighted average, okay, according to this formula, which is also pretty straightforward. And also, I guess also we've already seen this many times. So what is really new in today's talk is the following. I try to use a couple of simple examples to really show what it means. Even the rules looks pretty straightforward, but when you combine them together into a more complicated example, you will see something interesting. So we start with a very simple concept hierarchy with 4 concepts. Here you'll see that basically it means Tweety is a bird, bird is a type of, is a robin, and robin is a type of bird, bird is a type of animal. And here Tweety is put within curly brace. That's what we call extensional set. It's just because Tweety is a proper name. Compared to the others, they are common nouns. So the proper name needs some special treatment, which again is explained in my publication. Okay. Anyway, we just take the default truth value for all the input. Okay. It's kind of like, you see here, the confidence value doesn't really matter that much as far as they are the same. It basically say that I believe those 4 to the same level, okay, to make things simple. Now let's see what we can derive using the previous rules. Clearly from Tweety is a bird, bird, is a robin, robin is a bird, then we can derive Tweety is type of bird by deduction, okay? Which is, you see is based on the transitivity, or you can intuitively see this as kind of like combine these two links together into a direct link from one term to another one. But this time, you'll see the confidence level will be lower. So the conclusion is always weaker than the premise in terms of stability. Okay. The same thing here. You can say from robin is a bird, bird is an animal, then you have robin is a type of animal with the same confidence. And finally, of course, you can build this three together by using this as a premise. You already know Tweety is a bird and the bird is an animal, then Tweety is an animal. So this the conclusion of one step of inference can be used as a premise of the next step. That's also quite common in reasoning system. Here, the difference is since everything is true to a degree, then you have an even lower confidence in the conclusion. Okay, so this is the weakest conclusion among all the conclusions in this picture. So this is still pretty straightforward. Now the interesting starts. Let's see, where is the learning? You'll see, I mentioned that there are several types of learning happening in NARS. One is by induction. Induction, you can also call it a learning rule. Okay. Now let's see. We start from what we have obtained by deduction in the previous slide. Now we see this Tweety is a robin, is also a bird and an animal. But the truth value between these three pair are different because some of them are kind of like direct input, some of them are derived conclusion, which is weaker. But anyway, I hope this is easy to understand. And now, what if we know a property of Tweety? Say that Tweety is yellow. Again, this yellow is put this time in a square bracket because it's adjective. Adjective define a property so that it's different from noun. If you turn it into noun, you need a logical operator. So again, that's what we call intentional set in this context. Okay. So also the strength, you can see we are using the default truth value is 1.0 and 0.9, right? Just like this. Okay. Now the question is what you can derive from here. So if you compare with the previous patterns, you will see that this premise, this new information can be used together with each of the three to do induction. The pattern are the same. And what's the meaning, intuitively speaking? In this case, the meaning is we are generalizing or observation about Tweety into a category which it belongs to. Okay, that's typical generalization or induction. So for example, we can see that since we know Tweety is a robin and Tweety is yellow, we can get a conclusion, say robin are yellow. This clearly is not deduction. It's, in traditional logic, it cannot be justified. In NARS, it can be justified by interpreting the result as Tweety provide evidence for the conclusion that robins are yellow. Okay. If you only know one robin which happen to be yellow, of course, it's valid to think robins are yellow as far as I know. You'll see this is the truth value produced by the inductive rule, which I use this dashed line to indicate is weaker, is less confident. How about the other two? Actually, you'll see that the logical relationship are the same. So why not? You can actually derive the conclusion that bird are yellow and even animal are yellow, which may sound weird to us, but if you think about the logical relationship, they're equally valid. All three conclusions are valid. It just this one and this one are weaker and even weaker because you're kind of like generalizing further away from your observation. Okay, so this is something which is well known, that is, for the same observation, there are several different levels of generalization, or actually maybe you can argue there are infinite number of possible ways to generalize your observation. So that's related to a lot of topics studied in machine learning, which I put here. For example, what they call inductive bias. Okay, that's basically a way to pick one level of generalization among all possibilities, so that the others are either too low or too high. This one is the proper, or this one is kind of like more relevant to what I want to do. Okay, there is some value in that treatment, but you see that in NARS situation is different. Instead of picking which is the right generalization, NARS will, in principle, carry out all of them if there is enough resource. Okay. We know NARS doing a dynamic resource allocation based on the current attention. So in reality, it's possible that it will only produce this one, or it will only produce this one. But in principle, if we only think about the logic part, it will produce all of them, just because all of them are equally justified by this piece of evidence. Why we think this is weird? Like Tweety is animal, so if Tweety is yellow, all animals are yellow. Well, we feel strange is just because we know a lot of negative evidence for that conclusion, right? So we can deny this one in much easier way than to deny a less general conclusion like robins, if we happen to know all yellow robins only, right? So that also address another issue studied in machine learning, that's so-called transfer learning. Okay. In NARS, actually, there's no such a thing as transfer learning, because all learning, by definition, can be transferred. It just, in this case, you'll see that here you're going to transfer your knowledge about Tweety into all robins, and at this level, you're going to transfer it to all birds. And finally, you're going to transfer it to all animals. Okay, so it's by nature it will be transferred to other things, but a different level of generalization will transfer the result to different places. Okay, and also there is a big issue in machine learning, that's overfitting, right? Which basically in this picture means you are not generalizing enough. You're too close. Your conclusion is too close to your observation. Once again, in NARS, there is no such issue as overfitting. Even after you have all those conclusions, it's still valid for the system to stay with the observation, say that no matter what, I know pretty sure that Tweety is yellow, okay? Even though those generalizations may have different degree of belief, this one is believed stronger than all of them. Or I can still have a more stronger conclusion in a hypothesis which is closer to the observation compared to the one which is further away. So here, the important thing is to separate the degree of support and the degree of generalization and the degree of usefulness. They're all different. If you only talk about the degree of support, of course, you stay with the observation as close as possible. That's the safest generalization because it's going to be pretty strong. The conclusion will be strong. But on the other hand, it may be less useful. But how useful it will be, it actually is not determined at the time when you do generalization. It's something determined in the future in many situations. Say in this case, you derive the 3 hypotheses, you don't really know which one will really be useful in the future. Okay? So again, instead of trying to only pick one specific generalization, in NARS, all of them will be allowed So first, it will be the attention allocation mechanism to decide which one is more relevant to the current situation. Then in the long run, it's actually the feedback, the reward and the punishment, which will pick the most useful one, instead of trying to avoid overfitting from the very beginning. Okay, so that's one example. Another example is more about the revision. Important form of learning is you should be able to modify your belief in the face of new evidence. Okay, so now let's see how it is done in NARS. Okay. So first we start with this is the result of the deductive process. Now, what if I put it in another piece of evidence, which contradict to the conclusion here? Okay, you'll see here frequency zero means that this is a piece of pure negative evidence, which basically say that Tweety is not an animal. Let's just use the interpretation for this example. Just say, okay, Tweety is actually a cartoon character, okay, so that it's not an animal in a certain sense. Okay. So what will the system do if this is actually fit into the system as a part of its experience, or say social experience? Other people told it, you get it wrong. Then clearly that's a contradiction with not only this one. A straightforward treatment, of course, is to do a revision between this one and this one according to the revision rule, which we already know in the previous slide. Okay, so you get some kind of like weighted average because this one have a higher confidence value than this one. Then the conclusion you see, the frequency is more negative than positive. But this one still count. It's not use this one, just simply override everything you believe before, okay? As I said, it's a weighted average, but it's not a simple, use the confidence as a weight and compare the frequency. It's more complicated than that, but intuitively speaking, it's still a weighted average. But what makes a reasoning system complicated is their logical relations among the judgments. Okay, so we know this one is derived from a whole bunch of others. So to only modify that one, the conclusion itself does not really get rid of the implicit contradiction among the premises. And this is a well-known problem, actually, in traditional symbolic AI. Especially in the system using, say, non-monotonic logic. Okay. So some of you may know this name AMS. It's called Argument Management System that was developed in symbolic AI many years ago. Try to handle this kind of issue, which according to my opinion, it didn't work well. It's just because all of those attempts is trying to resolve this within binary logic. So what they do is they try to remove everything which is inconsistent with the new information under the assumption that the new information itself cannot be challenged, which I don't think it can be justified. Actually, Gardenfors and his colleagues also did something under the name of belief revision for the same issue, and I think have the same problem. But anyway, let's see how it's handled in NARS. So we not only use this negative evidence to modify this conclusion, we are going to go back to modify the premises which generate the conclusion. So first, we are going to actually use this one as one premise, and this one as the other. We are going to modify our belief about whether treaties are birds or whether robins are animals. Okay, it's just because you see that if you go back to the original picture, you see this conclusion is derived from these 3 original input. Okay? If the conclusion can be challenged, at least one of them should be challenged, or maybe all of them to different degree. Okay, that's actually is the attitude in NARS, that in NARS there's nothing absolutely true or false. Everything is to a degree. So this one, if this one is the product of 3 premises and all 3 of them will have some doubt or negative evidence introduced, but to different degree. Okay. So now you'll see that first we are going to first generate a negative relationship between Tweety and bird from this negative and this positive. And then we are going to use that to do a revision with the previous conclusion, and this is the final result. Okay, in this part, I skip the intermediate step. Otherwise, it just will be too complicated. And then we are going to do the same thing for this, and finally for this. Okay, so you'll see that that's kind of like the end. For this simple example, NARS can actually exhaust all possibility. So to make this clear, if you're interested, I actually have a spreadsheet prepared for this example. So you'll see here, this is the initial input. So from this initial input, we derived in the first slide the deductive conclusions with the truth value, and also here I mentioned where it comes from. Okay, so this input, each of this is from a pair of input by the deduction rule. Okay, then at this moment I gave you this negative evidence. Now you see this negative evidence is going to propagate within this network, okay, which produce a whole bunch of negative conclusion, actually between all of the conceptual relationship we have here. Okay, they're all negative because they're coming from one negative and one positive, either by abduction or induction. Later, I will share both files. If any of you are interested, you can check the detail. Okay. And also, yeah, since this is a spreadsheet, you can see the calculation here. And you can compare that with the formula I showed you before. Okay. So anyway, you're going to get a negative conclusion, but again, with different levels of confidence level based on the premise. Then finally, this is the first, the final stage that you combine this group with this group. You get the final conclusion by pairwise revision. Okay. At the end, you will see that each of them gets some negative evidence, but the consequence or the effect to the premise are different from case to case based on the factors involved, which actually, in a sense, is quite similar to backpropagation. Okay? But the details, of course, are completely different. But the overall effect is similar. So that if you make a sequence of decision and the result turn out to be wrong, then you need to go back to evaluate all the previous premise. Okay, then decide which one is the most probabilistic, dangerous or suspicious. Okay, then you modify. And I make it a spreadsheet also because you may want to play with it. For example, here I assume initially they're equally believable for the input. Okay, if I change that, for example, if I say the second one is less likely, and then the third one is even less, you will see many of the readout will be modified, especially if you check the final readout. Okay, you'll see it's not like in this picture anymore. So we're going to doubt this bird is a robin a little bit. We're going to doubt this Tweety is a robin a little bit, but we're going to challenge this bird is animal much more. Okay, just because it's kind of like it's the weakest link among the premise. So in the result, this one is challenged more than the other two, even though the other two also collect some negative evidence. Okay, and also you can try to change the frequency. You will see what happens in the result. So this is an example I think will give you a better idea about the overall effect of all the inference rules when they're combined together. Of course, in this example, I only talk about those 4 rules. In NARS, there are much more than that. Okay, but those 4 rules are the most typical ones. Now let's move to the larger picture. I think there are also a couple of points which now I can make using this example. This is a diagram I showed before in our previous meetings with some modification. You'll see that in NARS, everything is represented by a term, and a term is just a name of a concept. Okay, so the whole memory of the system can be seen as a concept network. Here in this picture, this blue link with arrowhead still represent what I call inheritance. So that the whole thing you see is an inheritance hierarchy. What is interesting in this hierarchy is we have several different types of terms involved. And also, yeah, this green two-way inheritance is what we call similarity, which is a two-way inheritance. Okay, so that so the inheritance go in both directions. Of course, this is also true to a degree. So in this picture, you can see there are several types of terms. Some of are directly related to the words in a human language. Here we have English, we have Chinese, of course we can have Italian and many other language involved. So each of the word or phrase can be handled as a concept, which you can think can be directly triggered by that word when you read or see it. Okay. Then what? Then we also have a bunch of things that directly come from your sensory motor. For example, this is a sensory, like whenever you see a picture, that picture, if it's represented within the system, that's also a term, which may correspond to a concept. That concept does not have a verbal name. Its name is just the picture itself. Okay? And also you can see there is also inheritance relation among those internal mental image or whatever you call it, or perceptions. Like for example, this bird is kind of like a generalization of this one and this one, because this two can be kind of like directly observed, and this one can only be in your imagination or abstraction or generalization from them. And then we also have a whole bunch of pure internal terms, which does not directly relate to any word or image, but it's not directly triggered by any of them, but it's related to them by inheritance and similarity, as well as many other things. Here we also have, say, operations involved, like you can control your sensor, you can control your actuator, and so on. Okay, so everything is in such a network. The difference is some of them is on the boundary. That's why I put a yellow frame around. Okay, this boundary can be both either a sensory motor boundary where you directly interact with the physical world, or is something defined by a natural language or human language, where you communicate with other people. Okay? So anyway, there's something in the boundary and something completely within the system. Here, I just use arbitrary IDs to indicate, they cannot be expressed to the outside, but within the system, it still makes sense because it's kind of like a summary of systems experience or related to them. Okay? And actually, by the way, it just occurred to me that I think this is related to what Antonio said about the three types of entities in his architecture. I think his symbols are close to what I call this verbal term. His sub-symbolic level is closer to what I have here as a sensory motor image. And finally, his concept in the middle, more like what I call internal terms. What make, so you'll see, I also recognize those differences, but what makes NARS different is at another level, even though there is this difference, at another level, everything is a concept and named by a term. And the inference rules among them are the same. Okay? Also, the meaning of a term is determined by its relation with other terms. Okay? For example, what this one means. This one, the meaning is partially revealed by its relationship with words in English and Chinese, and partially revealed by its relationship with image, as well as its relation with other terms. Okay? So if we zoom out to an even larger picture, we will see that that's my mental image about what NARS memory or even human memory looks like. It's a huge concept network. Their concepts relate to each other, and the difference is some of them are on the boundary. Okay? So that those things on the boundary can be directly activated from the outside, either through sensory motor interface or through linguistic interface, which is indeed looks like a neural network. But here the key difference is the semantics. Okay, what's the meaning of each of the concept? In NARS, it's very simple. It's completely determined by the relationship with other concepts. Okay? So that's why you see that I don't really fully agree with the idea of symbol grounding. Okay? So I don't think the meaning of a term is determined by something outside the system. Instead, it's within the system. It's its relation with the other things. And also, finally, what are this? This is, in my mind, how abstract concepts, or typical example, mathematical concepts, which also we discussed in our previous discussion, get into the picture. Okay? To me, those concepts, like, for example, we have, say, this is number theory, okay? And this is, say, geometry. And we also have concepts in those theories, and they have relationships which partially decide their meaning within that theory. But different from the other things in this network, they are not completely related or embedded into our experience. But we can say, yeah, it comes from experience originally. Of course, it cannot become anywhere else. But after we built them into a theory, their meaning become abstract, in the sense that they are relationship with the conceptual or empirical concepts become something you need to build each time when you apply this model into part of the problem, to solve your problem. And also a fundamental difference is you can have more than one interpretation or more than one usage, like in this picture. I have a theory which can be mapped into this part of my experience to solve some of the problem, which can also be mapped into this area to solve some completely different problem in a sense that those concepts and these concepts are in completely different domain, talking about different things. Okay, this is where I see the symbol grounding problem come originally, which actually is a valid problem. That is, mathematical concepts has no innate meaning, and its meaning is determined by its interpretation. Okay, different interpretation will assign them different meaning. So they're neutral in meaning, which actually give them the power to be used in different places to organize different experience. Okay? But to me, the problem about the symbol grounding debate is people confuse these concepts, what I call abstract concepts, with these concepts that what I call concrete concepts. Okay, yes, for math, the concept get their meaning by interpretation, but that's not true for our ordinary concept. Okay, they get their meaning by its relation or its role in experience, which also leads to what we call a second symbol grounding problem. That is, some people say, yeah, that's true, but eventually, even those concepts, their meaning is still determined by the related boundary term. Say, for example, they will say, birds meaning need to be reduced into the image, which I don't agree. I will say the image will contribute to the meaning, but not completely determine it, because even the meaning between abstract concepts also contribute, the relation between them also contribute to the meaning, okay? Or I will say, you see, this one gets some of the meaning, part of its meaning from its related sensory motor, but also another part of meaning from its relationship with other things, okay? You cannot say that only the sensory motor part make a contribution. That's wrong. So that's kind of like my mental image about this thing. And also another picture we can talk about is the learning process. You'll see that, go back to my previous example, you'll see all the change or new information initially appear at the boundary. Of course, it need to get into the system either through a sensory motor or through a language channel. And then it's going to propagate, again, as in my previous example, to the neighbors, to the other concepts related to it gradually. In my previous example, since there are only 4 concepts or 4 or 5 involved, I can actually exhaust all possibility. But in reality, it almost never happens in the human mind. It's just because, once again, it goes back to AIKR, right? The insufficient knowledge and resource restriction. So because of the real time and environment, each input is going to make some local change. And it's going to propagate. Well, how far away? Well, it's basically depends on the context, depends on attention allocation, and so on. But anyway, it's not going to go to the end. So most of the local change will be made, but the remote change will gradually happen, and some of them may never happen in a certain situation, even though all the premises are there. You just didn't get the time to link them together to make the conclusion explicit to yourself. So that's why that sometimes we can convince other people, which is basically to show them what their previous belief can be put together to derive something which they didn't realize, right? That's a quite common situation. So, and also that's related to my my opinion about understanding. That's an issue Chris also mentioned before many times, right? So in this picture, I gave you a piece of my message. Your understanding is basically the consequence it made in your mind. So which explains, even for the same message, in different people, they will have different understanding because their previous internal structures are different. and also because the time, the resource allocation are different, and so on. Okay, even for yourself, I give you the same relationship. How far it will propagate, also it can be different. To me, that's what understanding is really about. There are, of course, a whole bunch of details. Let me just summarize what I want to say using those examples. First is something we argued in a previous paper. Learning and reasoning in NARS is just the same thing. If you focus on the local step-by-step process, you treat it as reasoning. If you see the long-term consequence, is learning. The goal of the learning is very different from the current machine learning paradigm. Again, that's argued in detail in our paper. The current machine learning basically say learning is to approximate or optimize a function. In NARS, learning is to organize experience. It doesn't necessarily settle down to any function at all. It's just, that's why they call it self-organization. Okay. So that also I see many current machine learning problem is not really a general problem in AI. It's actually a problem specific to machine learning paradigm. For example, now people are talking about different types of learning, say transfer learning, left-wrong learning, cumulative learning, incremental learning with multi-goal, multi-hypothesis, multi-level of abstraction. I think at the very beginning, learning should be all of those at the same time. Okay, so machine learning community to me is kind of like first narrow down learning to a very special form and solve that, and then try to generalize the solution to the kind of like the real situation. To me, that's not a very fruitful approach. Finally, the result of learning, the knowledge you learn, it will never be absolutely certain or absolutely consistent. You'll see that in our, even after all the revisions, there is still implicit tension among the knowledge. So if you follow different paths of reasoning, you may get a different conclusion, which I guess is just a property of intelligent system. Okay, okay, that's all.